is well known that stars are huge, extremely hot, glowing balls of gas. But where do stars come from? Are there different types? And what happens to them eventually? We will attempt to answer these questions in a deep exploration of star formation. But first, some background. When we think of interstellar space, we often think of a cold vacuum of nothingness, but this is not strictly true. Between the stars in our galaxy is what is known as the interstellar medium, or in other words, the matter and radiation that exists between stars. It is comprised mainly of hydrogen, followed by a smaller amount of helium, and trace amounts of heavier elements such as carbon, oxygen, and nitrogen. Now, this interstellar medium does not have the same density throughout all of space, and the denser regions are called nebulae. From our point of view, nebulae may appear as holes in the night sky, but they are actually massive interstellar clouds of gas and dust, often several light years across. You may have seen this image before, known as the pillars of creation. What you're looking at is an example of these gas and dust clouds. Just for some perspective, what you can see of the far left pillar is over 4 light years long. However, this image is just a small section of a region called the Eagle Nebula, which is one of the many stellar nurseries where stars are formed in our galaxy. The pillars themselves are known as molecular clouds, the densest regions of the interstellar medium. These clouds are cold and dark, at around minus 260 degrees Celsius, and they don't allow light to travel through them very easily due to their density. Molecules are also spread out through these clouds, with their shapes being supported by a balance of their own gravity and internal pressure. It is these clouds of molecules and dust that turn into the same stars we see every night. But what exactly is the process? Generally speaking, these clouds are stable and would exist for billions of years without dramatic change. So in order for these clouds to become stars, there has to be a trigger, and there are a few different types of triggers that are thought to kickstart the process. If we take a look at the pillars of creation photo again, we can see one of these triggers in action. Along the outside of the pillars, you can see a slight glow of light around them. This is because ultraviolet light from hot and local stars is hitting the outermost molecules, exciting them to higher energies. These excited molecules either escape away from the cloud, or they push against the colder molecules further in, compressing them. This pressure can also be created by a supernova shock wave, molecular clouds colliding, or on a very large scale when galaxies collide. Any of these triggers can destroy the equilibrium or the balance of the cloud. Its internal pressure starts to give in to its gravity, and a gradual collapse begins. A kind of turbulence is created within the cloud that causes molecules to start to clump together under their own gravity, gradually growing bigger as their gravity increases and more molecules are pulled in. Depending on the size of the cloud, hundreds to millions of these clumps can be formed, and these are called protostars, the beginnings of real stars. As the molecular pressure increases due to the initial trigger, interaction between molecules increases, and the material at the center of these clumps begins to heat up. At this point, a domino effect of gravitational collapse occurs, with higher density causing stronger gravity, leading to an increase in both mass and temperature. At the same time, these protostars begin to rotate, gradually increasing in speed until the material surrounding them flattens out to become what is known as a protoplanetary disk. Clumps form within the disk as well, which can then turn into the protostars' planets or even become protostars themselves. They continue to gain mass as long as the molecular cloud surrounding them continues to feed them material, and once this material is exhausted, what is left behind ranges from 1 to millions of protostars born. Now, if the temperature at the center of these protostars gets hot enough, around 10 million degrees Celsius, it can induce nuclear fusion, which is a process that must take place for a protostar to be considered a real star. During nuclear fusion, 2 atomic nuclei combine to form a single heavier nucleus while releasing massive amounts of energy. In the case of stars, their high core temperatures allow the nuclei of hydrogen atoms to collide with enough energy to overcome the electromagnetic repulsion between them, leading to the strong nuclear force taking over and fusing the 2 nuclei. This process releases energy because the total mass of the resulting single nucleus is less than the mass of the two original nuclei. The leftover mass is converted to energy, as stated by Einstein's equation E equals mc squared. Only by colliding nuclei together and fusing them in its extremely hot core can a star release enough outward energy to counteract the effects of gravity crushing inward. This means that the amount of matter that forms the star determines the amount of fuel and therefore the lifetime of the star. Let's take a look at the reactions that occur during nuclear fusion in stars, which altogether form a process called the proton-proton cycle. The first step in the process is two hydrogen atoms reacting to form a deuterium, which is a stable isotope of hydrogen with one proton and one neutron. The neutron needed to form the deuterium is created when one of the two original hydrogen atoms undergoes beta plus decay, a process in which a proton is converted to a neutron, producing a positron and a neutrino, which are other subatomic particles. After this deuterium is formed, it then reacts with another hydrogen atom to form the helium-3 isotope, producing a gamma ray in the process. The final step in the chain is two helium-3 atoms reacting to form one ordinary helium and two ordinary hydrogen atoms. This process of hydrogen converting to helium happens constantly, at least until the hydrogen is exhausted, and is what creates the pressure needed to keep the star from collapsing under its own weight, and the energy by which it shines.
Stars are primarily classified based on their mass and temperature. There are three main types of stars. Main sequence stars, which are stars that have an ample source of hydrogen and are in the prime of their life. Red giants and white giants. Throughout a star's lifetime, they will transition between these three main types of stars. However, there is also a spectrum that classifies 7 different types of stars based on their increasing temperature. From this, they are assigned a specific spectral type. This goes as follows: O, B, A, F, G, K, M. O being the hottest and M being the coolest. This spectrum is known as the Morgan-Keenan system and was founded and established in 1943. Moving on to the life cycle of stars. A star's life is dependent on its mass. As the higher mass, the shorter the life because it will typically burn out its fuel more quickly, while lower mass stars tend to have a longer lifespan as they will ration their fuel. A star following its formation begins its young life in nuclear fusion. This star is young and known as a main sequence star. As a star burns up the hydrogen in its core, it begins to slowly cool and expand. If the star is big, it will turn into a super red giant. If the star is of average mass, it will turn into just a regular giant. Following this is where we see a major differentiation between the stars and life cycle based upon their mass. Red giants will slowly cool down and enter the planetary nebula and white dwarf phase, where the star shrinks and becomes hot. Opposite the super red giant will explode into a supernova at the end of its life cycle, and this collection of gas that remains after the explosion can be utilized as a nebulae cloud to fuel the next generation of stars.